So for today's agenda, we're going through ionic bonding, okay, the structure and properties of ionic compounds, and then there'll be MCQ questions for you to try, and then covalent bonding, and this for both simple and giant covalent molecules. Okay, they will go through the structure and properties as well, and there will be MCQ and structure questions at the end. Okay, and finally metallic bonding. So these three different types of bonding, and then the structure and the properties. Okay, and there'll be MCQ and structure questions. So at the end, I'll let you know about what it's like to be in a weekly tuition class over here, and there'll be a feedback form in the end. So just to let you guys know, I charge $80 for 2-hour lesson, but I'm doing this for free. Okay, so all I ask in exchange is just to fill up the feedback form. Okay, so I can improve and so I know what students like. Okay, so at the end, there will be a feedback form. Okay, and at the end, I'll also answer some of the questions you all have. Okay, so before we begin, I want you guys to remember this term. Okay, this term is valency. So valency is the number of electrons an atom can gain, lose, or share in order to achieve a stable electronic configuration. Okay, so stable electronic configuration means that the valence shell, the outermost shell, is filled up with electrons. Okay, so for the first shell is 2 electrons, for the second shell is 8 electrons, and the third shell is 8 electrons. Okay, that's the stable electronic configuration. So the number of electrons you can gain, lose, or share, that's the valency. So let's look at this table here, okay? So for group 1, 2, and 13, right, they are your metals. Okay, so these from group 1 to group 13, the valency will basically be the digit, the last digit. So group 1, valency is 1, group 2, valency is 2, and group 13, the valency is 3. So for metals, right, they have a tendency to lose electrons to form positive ions. Okay, they have a tendency to lose electrons to form positive ions. Because your metals, right, they have from group 1, 2, and 13, right? So they have 1, 2, and 3 valence electrons. So they are more likely to lose the valence electrons than gain, correct? So they have a valency of 1, 2, and 3. Okay, then let's look at your non-metals. So your non-metals are from group 14 to 17. Okay, 14 to 17. The valency of these will basically be 8 minus the last digit. That means the valency for group 14 elements is 8 minus 4, okay, which is 4. Then for 15 is 8 minus 5, which is 3. Then 8 minus 6, which is 2. And 8 minus 7, which is 1. Okay, so for non-metals, they will either gain electrons or share electrons. So usually they don't lose electrons because they're non-metals, they have more valence electrons. So it's easier to gain and share electrons compared to losing electrons. Okay, so they have a higher tendency to gain electrons or share electrons. So group 15, they will have a valency of 3 and not 5. Okay, because they have group 15, they have 5 valence electrons. So it will gain 3 or share 3 to achieve 8 valence electrons, which is the stable electronic configuration. So I want you guys to remember the meaning of valency, and we're going to use this table later to check the valency of various elements, okay, so that we can understand better. So we're going to start with ionic bonding. So for chemical bonding, right, what is the purpose of that? Is to achieve stable electronic configuration. Okay, achieve stable electronic. So most of your elements in the periodic table, basically all of your elements except for group 18, your noble gases, they do not have a stable electronic configuration. Okay, they do not have a full valence shell. So the purpose of chemical bonding is to achieve this stable configuration. So there are 3 types. You have ionic bonding, you have covalent bonding, and metallic bonding. Okay, so we'll start with ionic bonding. Okay, ionic bonding is the transfer of electrons from metals to non-metals. Okay, so transfer of electrons means that one atom will lose electrons, the other one will gain electrons. So in this case, the one that loses electron is metals. Okay, remember I mentioned that metals have a higher tendency to lose electrons. So they are the one losing electrons when ionic bonding occurs. Okay, then non-metals will be the one that gains electrons. Okay, so let me write down lose electrons, and non-metals is gain electrons. Okay, so as you can see in this example, we have lithium and fluorine. Lithium and fluorine. So now we'll use valency. Okay, we'll find the valency of lithium and fluorine by itself. So lithium, right, is in group 1. So the valency is 1. Okay, because it has one valence electron, so it will lose one valence electron. So the valency is 1. Okay, then we look at fluorine. Fluorine is in group 17. So is the valency 7 or 1? The valency is 1. Why? Because non-metals, they don't lose electrons. So you're not going to lose 7 electrons. You're going to either gain 1 or share 1. Okay, so in this case, it's going to gain 1, but still the valency will be 1. Okay, so valency of fluorine is 1. So what is the purpose of finding the valency? So that we know the bonding for ionic bonding. So if the valency is the same, that means the chemical formula is just one of each. So one lithium atom, one lithium, and one fluorine. Okay, so let's look at how it works. So lithium, it has one valence electron here. It will be transferred to fluorine. Okay, it's that simple. Basically, the electron here transferred to fluorine. So if the valency is 2, it transfers 2 electrons. If the valency is 3, it transfers 3 electrons. Okay, but in this case it's 1, so it transfers 1 electron. And then fluorine, it gains 1 electron from the lithium. Okay, so it's the same electron that is being transferred. And how do you draw the bonding? First, you draw the new structure. So lithium, originally it has 3 electrons, correct? So the configuration is 2, 1. 2, 1 is the configuration. Okay, so 2 electrons in the first shell, 1 electron in the second shell. Then fluorine, it has 9 electrons. So the configuration is 2, 7. So it has 7 valence electrons. Okay, so lithium, it will lose 1 electrons. So the new configuration is 2. So you'll just draw a circle with lithium inside and 2 electrons. Okay, then you'll draw a bracket. So make sure that the bracket covers the whole ion. Okay, then after you draw the square brackets, the top right-hand corner will be the charge. So how do you find the charge? The charge is basically whether it loses or gains electrons and how much it loses or gains. So if it loses electrons, right, it's a positive charge. Okay, and since lithium loses 1 electron, it is a 1 positive. So 1 plus. But in chemistry, we don't write the 1, so it's just a plus. Okay, then for fluorine, right, fluorine gains 1 electron. This is the 1 electron here that it gained from lithium. So you draw this, and then you draw the brackets again, and the charge. So for fluorine, it's a non-metal, so it will gain electrons to form a negative ion. And how many electrons did it gain? It went from 7 to 8, so it gained 1 electron. Okay, so the charge is 1 minus, which is minus. Okay, so there's an error here. It says non-metals lose electrons. I want you to change it to gain. Okay, so metals lose electrons to form positive ions, and the non-metals will gain electrons to form negative ions. So that is it with the drawing of diagram. Now we move on to the actual bonding. Okay, so the bond between the positive and the negative ion is called ionic bond. Okay, so the ionic bond is the strong electrostatic force between the oppositely charged ion. So between the positive and negative ion. Okay, then a compound which contains ionic bond is called an ionic compound. Okay, pretty self-explanatory. And this compound, right, the structure is a giant ionic crystal lattice structure. Okay, so this is the structure. Structure. So it looks something like this. So I want you to think of this analogy. So pretend during peak hours, right, the MRT is very crowded. Okay, so the MRT is like the whole structure itself, the lattice structure, and then inside there's a lot of people, right? So they are like stuck there together, they cannot move because all the seats are taken, then everybody else has to stand. So they're basically stuck, they can't move around the MRT. Okay, so the people are your ions. Okay, so pretend you have the MRT, then these lines are all the people. Okay, so they are like all stuck at one place, held together, they cannot really move. Okay, so think of the people as the ions. The ions are all held together by very strong electrostatic force. Okay, between the oppositely charged ions. So you know magnets, right? North pole is attracted to the south pole. Same thing for ions. Positive attracted to negative. Okay, so positive and negative, there will be a very strong attraction, a strong electrostatic force. Okay, so that's the bonding. So this is how the structure looks like for sodium chloride, for example. Okay, and then this line over here, right, is the ionic bond, which is also the electrostatic force, the attraction between the positive ion and the negative ion. Okay, so you see the ions are like held together, they can barely move. They can't even move. Why? Because the force is just too strong, they're holding it together. Okay, so that's the structure in a solid state of ionic compounds. Now we move on to the physical properties. So they have high melting and boiling point. So why they have high melting and boiling point is because, remember I talked about the attractive force between the ions? Opposites attract each other, right? So positive and negative, there will be a very strong attraction. So since the electrostatic force between the positive and the negative ion is very strong, so you need a lot of energy to overcome it. Think of it like you lifting weights, right, in the gym. So when you lift weights, the heavier the weight, the harder it is to lift, right? So it requires more energy. Same thing for this. There is a strong electrostatic force between the positive and the negative ion. So since it's very strong, it requires a lot of energy to overcome the force. That's why ionic compounds have high melting and boiling point. Okay. Then we move on to the second property, which is they conduct electricity only in molten or in aqueous solution. So if you're confused, right, molten is the same as liquid. So it's basically saying it conducts electricity in liquid state. Okay. Then aqueous means that the ionic compound dissolves in water to form the aqueous solution. Okay, so it only conducts electricity in these two states: molten state, or basically liquid state, and then aqueous solution. So why does it conduct electricity in these states? Remember I talked about the crowded MRT, right? So the MRT is crowded, but when the doors open, the people can move freely, correct? So when the people can move freely, they are like the ions. The ions can move freely to conduct electricity. Okay, so when the doors open, the giant ionic lattice structure is basically being broken down. Okay, so it's being broken down only in molten or aqueous solution. And when it's broken down, the people can move about freely, just like the ions, to conduct electricity. Okay, so the ions can move about in molten and in aqueous solution because this giant lattice structure is broken down. Okay, so when the MRT open the doors, they can move, the people can move freely. So electricity can be conducted when the ions move about freely. Okay, whenever we talk about conducting electricity, it's either free moving ions or free moving electrons. Okay, if there's none of those two, then it cannot conduct electricity. So from what I said, right, obviously in solid state, it cannot conduct electricity. Why? Because in solid state, there is strong electrostatic force between the positive ion and the negative ion. So they are like held together very tightly at fixed positions. So it cannot move around to conduct electricity. Okay, just like the crowded people in the MRT, they cannot move around. So the ions cannot move around to conduct electricity. Okay, so that's the second property. The third property is it's generally soluble in water, but insoluble in organic solvents. So there's not really an analogy to remember this, but we can use common sense. So ionic compounds, right, they are generally soluble in water. We actually already know this. Why? Is because it conducts electricity in aqueous solution. What is aqueous solution? Aqueous solution is the ionic compound dissolved in water, right? So it already give you the answer. It can dissolve in water. Okay. Then the only thing you have to remember is it cannot dissolve in organic solvents. Okay, so they are soluble in water but insoluble in organic solvents. Ionic compounds are hard because of the strong electrostatic forces holding the ions together. So it's a similar explanation to why it has high melting and boiling point. So all the ions here, right, the positive and negative ions, they're held together by strong electrostatic force. So it requires a large amount of force to actually break apart the force. Okay, so that's why ionic compounds are hard. Okay, but they can be brittle. So what does brittle mean? Brittle means it breaks easily. So why is it brittle? When originally you have positive, negative, positive, negative, positive, negative. So you have positive, negative, they always attract each other. There will be a very strong electrostatic force. But once a strong force shifts the ions, right, then suddenly you have positive, positive, negative, negative. So positive and positive, will they still attract each other? No, right? They will repel each other. So these repulsive forces will actually cause the ionic bonds to break. Okay. So the ions of the same charge will repel each other and then it will overcome the attractive forces. So that's how the lattice structure breaks apart. Okay. And finally, in an ionic compound, the bigger the charges on the ions, the stronger the electrostatic force. So this means the melting and boiling point is also higher lah. So for example, right, we have magnesium oxide. It contains Mg2 plus ions and O2 minus ions. So let's focus on the charge here. We have 2 plus and we have 2 minus. Okay, then for sodium chloride NaCl, you have Na plus, Cl minus. So which charge is bigger? The 2 plus and 2 minus, right? That means the electrostatic force is also stronger. So with stronger electrostatic force between the ions, it has higher melting and boiling point because it requires more energy to overcome the force. So melting and boiling point is a measure of the amount of energy needed to overcome the force between two particles. Okay, so I hope everybody is clear. Then can you guys try question 1 and question 2? I'll give you 2 minutes for each question, so total 4 minutes. Okay, I will start going through the questions. Okay, question 1. An element M reacts with chlorine to form a compound MCl3. Okay, so MCl3 can conduct electricity in molten and aqueous solution only. Okay, so it says conduct electricity in molten and aqueous solution only. So this automatically tells us that it is an ionic compound. Okay, ionic compound. Because only ionic compounds can conduct electricity in these two states only. Okay, so what could be the electronic configuration of M? So ionic compounds, they are made of metals and non-metals, correct? So MCl3, Cl is chlorine. Chlorine is the non-metal because it's in group 17. Okay, so if chlorine is the non-metal, M has to be a metal. Okay, which means that M is probably in group 1, 2, or 13. Okay, so we can immediately eliminate options A and B. Because A and B, the configuration is 285 and 25, which means there's 5 valence electrons. Only group 15 elements have 5 valence electrons. Okay, so they are non-metals, which does not fit the criteria of M. Okay, so you have C and D left. If we look at the compound, right, it's MCl3. Charge of chlorine is 1 minus, correct? Because it's in group 17. So it will gain 1 electron to form a charge of 1 minus. Okay, but you have 3 chlorine ions. So what's the total charge? 3 minus. Okay, because 3 times 1 minus. So if chlorine is 3 minus, in order to balance out the charges, M has to be 3 plus. Okay, M has to be 3 plus. So it means that the valency of M is also 3. Okay, it shows that M loses 3 electrons to form M3 plus, which is the ion. And this also shows that the M has 3 valence electrons. So your answer is C. Okay. So D is out because it only has 1 valence electron. So, but M has a charge of 3 plus. Okay, so your answer is C. Because it has 3 valence, it will lose the 3 to form M3 plus. Okay. Then we have question 2. Which statement best explains why sodium chloride has a high melting point? High melting point. So melting point is a measure of the amount of energy needed to break a force or overcome a force between the particles. So let's read the options. The chemical reaction between elements sodium and chlorine is vigorous. So vigorous chemical reaction doesn't mean that it has a high melting or boiling point. Okay, it just means that it is reactive. Okay, so A is wrong. It just means that it's very reactive, sodium and chlorine together. Okay, then we have the crystallized lattice of sodium chloride has the same structure as diamond. Okay, firstly, having the same structure as diamond doesn't make it high. Firstly, they don't have the same structure. Right? Diamond is a giant covalent structure. Then sodium chloride is ionic. Sodium chloride has a giant ionic lattice structure. Okay, this one is giant ionic lattice. This one is giant covalent structure. Okay, 2 different structures. So it doesn't answer the question as well. So it's out. There are strong electrostatic forces between sodium ions and chloride ions in a crystallized lattice. This mentioned the strong electrostatic forces. So the stronger the forces between 2 particles, right, the higher the more energy you need to overcome, which means it has a high melting and boiling point. Okay, so C is your answer because it mentions strong electrostatic forces between the 2 ions, sodium ions and chloride ions. So it needs a lot of energy to overcome that force. Therefore, it has high melting point. Okay, then option D, just to double check, there are delocalized electrons in crystallized lattice of sodium chloride. Wrong. Because delocalized electrons is talking about the electrical conductivity. So whether it conducts electricity or not about the melting point. Okay, so your answer is C. So are there any questions for the first 2? So you just give me an emoji if you are okay with moving on. Okay, then we are done with ionic compounds. Okay, it's pretty simple. Then we'll move on to simple covalent molecules. Okay. Okay. So covalent bonding is the sharing of electrons equally between atoms of non-metals. Okay, so only non-metals. And again, what's the point of bonding? To attain the stable electronic structure. Electronic structure of a noble gas, also known as the stable electronic configuration. Okay, so it's sharing of electrons. What is sharing? Sharing, that means that there isn't a gain in electrons or there isn't a loss of electrons. They both share equally. Okay, so the number of covalent bonds depends on the number of pairs of shared electrons. So single bond means there's 1 pair of shared electrons. Okay, for example, H, single bond H. Then double bond means 2 pairs, and triple bond means 3 pairs. Okay, so let's look at example. For hydrogen, right? Hydrogen, what's the valency of hydrogen? It's 1 because it has 1 valence electron. Okay, so you either lose, gain, or share that one electron. Okay, so in this case, it's covalent bonding, so it'll be sharing. So you have two hydrogen atoms here, right? It'll be sharing equally because that's how covalent bonds work. So equally means that if this hydrogen shares one electron, the second hydrogen had to also share one electron. And that forms what? That forms one pair. Okay, and one pair means one single bond. So one pair is basically two electrons, but one single bond. Okay, so this is how it will look like. Basically, the two atoms will intersect each other, and then the electrons will be drawn in the intersection. So this is the electron of the left hydrogen, and this is the electron of the right side hydrogen. Okay. So in the end, what they want to achieve is a stable electronic configuration. So hydrogen now has two electrons on the valence shell, which is the full valence shell for the first shell. Okay. So now it's in stable electronic configuration. So it can be represented as H, single bond H. Why? Because there's one pair of shared electrons, which also mean one single bond. Okay? So a single line represents a pair of shared electrons. Okay. Then for different covalent bonds, right, you might have different valency. So let's say you have a valency of 2. Okay. Then another, let's say A has a valency of 2. B is a valency of 1. So what will be the bonding in A and B? It will be B, single bond A, single bond B. Why? So valency of 1 means it can share one electron. Okay. So each B atom, right, it will share one electron with A, and this B atom will share one electron with A. Okay. But A has a valency of 2. So it can share 2 electrons to reach its stable electronic configuration. So it shares one with B and it shares another one with B. So why can't it just share 2 with B? Because remember, the sharing of electrons have to be equal. So if B shares 1, A can only share 1. If the other B shares 1, A can only share 1. That's why here we have one A atom and 2 B atoms. Okay, so the covalent compound, right, is basically how you get the chemical formula is basically swapping the valency. So if A has a valency of 2 and then B has a valency of 1, the chemical formula will be swapped. Okay, so instead of A2B, it will be AB2. That will be the chemical formula. Okay, then of course 2 is slightly below B. Okay, and this is the bonding. B single bond A, single bond B. Okay, then we move on to the physical properties. So simple covalent molecules, right, they have low melting point and boiling point. Why? Is because the intermolecular force between the molecules is very weak. So intermolecular force already tells you that it's between the molecules, because intermolecular. So this force between the molecules is very weak. So the weaker the force, the less energy is needed to overcome it. Okay, we use back the lifting weights analogy. So just now I mentioned the heavier the weight, the harder it is to carry. So it requires the most amount of energy. But the lighter the weight, the easier it is to carry, right? So it requires less energy. So since the intermolecular force between the molecules is weak, it requires less energy to overcome it. That's why simple covalent molecules have low melting and boiling point. Okay, the second physical property is it cannot conduct electricity at all. Okay, at any state. So remember, just I mentioned for conducting electricity, there are only two things that you need to think of: ions or electrons. Okay. So either one of these have to be free to move. So you either have free moving ions, free moving electrons, or both. Okay, if none of those can move, then it cannot conduct electricity. So covalent compounds, they do not have ions. They also do not have free electrons. They do not have delocalized electrons. So delocalized means free to move. Okay, so they do not have ions, they do not have free electrons to move about. So simple covalent molecules cannot conduct electricity. Okay, so that's the second property. And the last property you need to know is they are generally soluble in organic solvents, but not in water. So how I like to think of it is just opposite of ionic compounds. Ionic compounds, they are soluble in water, but insoluble in organic solvents. So covalent is opposite. Simple covalent is opposite. Simple covalent is soluble in organic solvents, but insoluble in water. Okay. Right. So can I have you guys try question 3 and 4? And this time I'll give you 5 minutes. That's a good question. So you said if simple molecular substances are soluble in organic solvents, then wouldn't they dissociate to form mobile ions? Okay, so we look at simple molecular substances. So for simple molecular substances, right, once they combine with each other, they have basically a full valence shell. Okay, so firstly, there will be no free electrons to move. And then secondly, right, for simple covalent bonding itself is the sharing of electrons. So there is no gain or loss in electrons. So there cannot be any ions. Okay, in order for an ion to form, right, the atom has to either lose electrons or gain electrons. So if we look, for example, your metals, so let's just say sodium. In order for sodium to form a sodium ion, right, it has to lose one electron, okay, to form sodium ion. Then chlorine. In order for chlorine to form a chloride ion, it has to gain one electron. Okay, but there is no gaining or losing electrons in covalent bonding. Covalent bonding is a sharing of electrons. So when you share electrons between the atoms, right, no ions will be formed. So there is no possible way to dissociate to free moving ions, to form free moving ions. Yeah. Okay, I'm going to go through the questions now. So the diagram below shows the arrangement of electrons in a molecule of compound P2 cube. Okay, so from the diagram itself, I can immediately tell that it is a covalent compound. Okay, covalent compound. Because there is the intersection of the atoms. Okay, because there's intersection, right? There is sharing of electrons. Okay, they're only covalent compounds, they have sharing of electrons. Okay, so another thing it told me that is that all the atoms are non-metals. Okay, so if I see any metal in the options, I know it's definitely wrong. Okay, so which pair of the elements is correct? There are two ways to do this. I'll go through the first way. The first way is just to look at the number of valence electrons. Okay, so P, it has 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. Okay, P is the dot. It has 7 valence electrons. So it will have to be an element from group 17. So you only have chlorine and fluorine. Okay. Oxygen is in group 16, so it has 6 valence electrons. Sulfur is in group 16 as well. Okay, so 6 valence electrons. So you are stuck between B and D. Okay, then let's look at element Q. Element Q has 1, 2, 3, 4, 5, 6. 6 valence electrons. So it has to be in group 16. So oxygen is in group 16, but nitrogen is in group 15. Okay, so nitrogen is out, which means that B is your answer. Okay, so that's the first way to solve it. The second way is to look at the valency. So how many electrons are actually being shared? If we look at P, right, P here shares 1 electron. So the valency is 1. Okay, valency of P. Let me write it here. Then let's look at Q. Q is the cross, okay? There's one cross here and there's one cross here. So it shares 2 electrons. So the valency of Q is 2. Okay. So we just have to find the element with a valency of 1 and element with a valency of 2. Okay. And there are only 2 types of elements. For valency of 1, it's either group 1 or group 17. And we know it can't be group 1 because these are non-metals. Group 1 are metals. So it's definitely from group 17 now. So again, it's either chlorine or fluorine. Then valency of 2, right, is either group 2 or group 16. And again, group 2 are metals, so it's out. So group 16, you have oxygen and nitrogen. Oxygen is the correct answer. Okay, so B is your answer. All right, question 4. How does an ionic compound differ from simple covalent compound? Okay, state 2 differences. So usually when they ask difference questions, most of the time they're looking for properties. Okay, so let's talk about properties. First, ionic compound. Okay, in terms of melting and boiling point, which is the first property I always talk about when I mention the bonding, ionic compounds have high melting and boiling point. But simple covalent, they have low melting point. That's because the difference in the forces. Okay. What's the second difference? So we can also talk about electrical conductivity. Okay. So ionic compounds, they can conduct electricity both. Okay, but for simple covalent, it only conducts electricity. It doesn't conduct electricity. Okay, so that's the 2 main differences. Ionic compounds conducts electricity in both molten and aqueous solution, but simple covalent, they do not conduct electricity. Okay, there's one more difference. If you wrote this one, it's also correct. So ionic compound is soluble in water, insoluble in organic solvents. Simple covalent, soluble in organic solvents, insoluble in water. Right. So any 2 of these 3 differences is accepted. Okay. So when you guys are ready to move on, you can just give me the emoji again. Okay, great. Okay, so we talk about simple covalent molecules. Now is giant covalent. So giant covalent, right? The difference is that they have large number of atoms because it's giant ma. So they have a large number of atoms covalently bonded to each other. So it's like a network of strong covalent bonds. Okay, so the covalent bonds are between the atoms. Okay, it sounds like very obvious, right? Between the atoms, but no, because simple covalent substances, right? They have weak intermolecular forces between the molecules. So for simple covalent, it's between the molecules. But for giant covalent, we talk about between the atoms. They have strong covalent bonds. Okay, that's why giant molecular substances have different physical properties compared to simple covalent molecule. Okay, so let's get to diamond and graphite. These are the 2 that you need to know. So they are allotropes of the carbon element, which means they have different structures, but they are formed by carbon. Okay, so the bonding for diamond is 1 carbon atom covalently bonded to 4 other carbon atoms. Okay, So one carbon atom covalently bonded to 4 other carbon atoms, and it has an extremely high melting point. So based on the analogy I used just now again, lifting weights, the heavier the weight, the more energy you need to lift it up. So now there is strong covalent bonds between the atoms. So it requires a large amount of heat energy to actually overcome these strong covalent bonds. That's why diamond has an extremely high melting and boiling point. Okay. Diamond cannot conduct electricity. Okay, this is the second property. Diamond cannot conduct electricity because it does not have delocalized electrons or ions. Okay, again, conducting electricity, you need to have either free ions to move or free electrons to move. So just now, I mentioned that for covalent substances, there are no ions because there's no gain or loss in electrons. So no ions are formed. Okay, and it doesn't have delocalized electrons. Why? Is because each carbon atom is bonded to 4 other carbon atoms. If we look at the periodic table, right, carbon is in group 14. So it has a valency of 4, which means it can form 4 single bonds only. It can share 4 electrons. After sharing 4 electrons, it cannot share anymore. Okay, so that's the maximum. That means all the electrons are already being used up. Okay, if all electrons are used up, none of them, there's no leftover that is free to move to conduct electricity. So there are no free electrons and no free ions. Therefore, diamond cannot conduct electricity. Okay, it is very strong and hard. This is the third property. Same reason as why it has a high melting point. Because there's strong covalent bonds between the carbon atoms. So it requires a large amount of force to overcome the bonds. That's why diamond is strong and hard. Okay, so since it's so strong and hard, it is usually used as a cutting tool. Okay, fourth property, diamond does not dissolve easily in any solvent. Okay, so your water, your organic solvents, it doesn't really dissolve. Okay. Then lastly, silicon dioxide, it actually has similar structure as diamond. So it has like one atom here covalently bonded to 4 other atoms. Okay. So this is the structure of diamond, and the lines in between the atoms, right, they are your covalent bonds. Okay, these covalent bonds are very strong, so they hold the atoms together very tightly. Okay, so it requires a lot of heat energy to break these bonds. So that's why diamond has high melting point. Okay, so that's for diamond. Now we move on to graphite. So graphite is made out of layers of planes, which consist of carbon atoms. Okay, so they form these hexagonal rings. So look something like this. Okay, you have your covalent bond between the atoms. Okay, so each carbon atom is covalently bonded to 3 other carbon atoms. Here's the first difference. Diamond, each carbon atom is bonded to 4 other carbon atoms. But graphite, each carbon atom is bonded to 3 other carbon atoms. Okay. And I mentioned that carbon has a valency of 4. Right. Carbon valency is 4. So if it bonds to only 3, it still has space to bond one more, but it didn't. So there will be carbon atoms which are not bonded. And for every carbon atom not bonded, there's 1 electron. Okay, this 1 electron is very special because it can actually be used to conduct electricity. So there's 1 electron from every carbon atom which is not bonded, and these are said to be delocalized, which means free to move. So they can move about and conduct electricity. Okay, so graphite is able to conduct electricity. And one important point there is it is cheaper than copper. So if the question asks you why do people use graphite instead of copper when as the conducting material, then you say it's cheaper. Okay. Okay. Then for each layer of graphite, right? Each layer is held by weak intermolecular force. So it's like this line over here. These are your graphene sheets, and in between the sheets, right, the layers is weak intermolecular force, which means that it's easy for the layers to slide over one another. Okay, because it's easy, They are soft and slippery. They are soft and slippery. Okay. So it makes it suitable for graphite to be used as lubricants or pencil lead. Okay, because they have the properties of being soft and slippery. Okay. And you realize they never talk about high melting point or boiling point, right? Because it's the same as diamond. It also has high melting point because of the strong covalent bonds. Okay, so all giant covalent substances, they have these strong covalent bonds between the atoms. Okay, so if it has strong covalent bonds, it requires a large amount of energy to overcome. Therefore, it has high melting point. Okay, yeah. Now, can you guys try question 5 and 6? So just a little change here. Change this graphite to diamond. Okay, for option D. Then I'll give you 5 minutes, so we'll be back at 9:03. Okay. Okay, in simple molecular substances, right? We will never talk about the atoms. So in simple molecular substances, it's always just the weak intermolecular forces of attraction between the molecules. Okay, so there is no strong covalent bonds between the atoms because is a simple covalent substance, it's very small. It's not like a large network of covalent bonds. But for simple covalent molecules, there is intermolecular forces between the other molecules. Okay, and these intermolecular forces are weak. Okay, but there's no bonding. We don't talk about the bonding between the atoms for simple lah. For simple molecular. Yeah. Then for giant, they have strong covalent bonds. So all giant molecular substances, they have strong covalent bonds between the atoms. Okay. Okay. So I will also answer a previous question at the top by Claudia. So you mentioned you wanted to know the differences between simple covalent and giant covalent. So here's the first difference. The first difference is the bonding. Okay, so for simple covalent, the bonding is weak intermolecular forces between the molecules. Okay, then for giant covalent, the bonding is strong covalent bonds between atoms. Okay, then only you have one exception, which is graphite. Graphite also has strong covalent bonds between atoms, but they also have weak intermolecular forces between the layers of graphene. Okay, you just have to remember between the layers. Okay, so graphite, they have weak intermolecular forces between the layers, but they also have strong covalent bonds between the atoms. Okay, so the layers and atoms are two different things. The atoms are this circle thing. Okay, then the covalent bond is this line, but this dotted line here is the weak intermolecular force. Okay, so these are the two differences in bonding. So from this, it also tells you why they have different melting points. Simple covalent, weak intermolecular force, right? So less energy is needed to overcome. So low melting and boiling point. And then giant covalent, strong covalent bonds is harder. It requires more energy to overcome. So high melting and boiling point. Okay. Okay, let me go through the questions. So which is better to use as a cutting tool, graphite or diamond? So cutting tool, we need something hard or strong. Okay. And we learned that diamond is hard and strong. Okay. So answer is C. So why is diamond hard and strong? Because it has strong covalent bonds between the atoms. Okay, which requires a lot of energy to overcome, a lot of force to overcome. That's why diamond is strong and hard. Okay. Graphite is soft and slippery because it has weak intermolecular forces between the layers. So it's easy to slide past one another. Okay. So the answer is C, diamond, because it's strong and hard. Okay. Question 6. Diamond and graphite are made out of carbon atoms only. Explain why diamond cannot conduct electricity but graphite can. Okay. So in diamond, right? One carbon atom is bonded. 4. One carbon atom is bonded to 4 other carbon atoms. So it leaves no free or delocalized electrons to move and conduct electricity. Okay, so there's the valency of carbon is 4, and all 4 bonds are already there. So there's no free electrons to move and conduct electricity. But in graphite, one carbon atom is bonded to 3 other carbon atoms. So just one simple change from 4 other carbon atoms to 3 other carbon atoms, it leaves one free electron per carbon atom, not bonded. And their free electrons can conduct electricity. Okay, so I repeat, in diamond, one carbon is bonded to 4 other carbon, so there's no free electrons. But in graphite, one carbon atom is bonded to 3 other carbon atoms. So there's one free electron from each carbon atom that is not bonded. Okay, then those free electrons all together, they can move and conduct electricity. Okay. So you guys can copy this down, and if you are done, you can send the emoji again. Okay, since we're at this topic, right, I'll go through one more difference between simple covalent and giant covalent. Okay. So another difference we can talk about is the solubility. Okay. Simple covalent soluble in organic solvents, but insoluble in water. Okay. For giant covalent, they are generally not soluble in any solvents. Okay, so these are 2 differences that you can write down if the question asks you for the differences between simple covalent and giant covalent. So whenever the question say like explain in terms of bonding and structure, bonding you talk about the forces between the atoms or the molecules or the ions. Okay, so for simple covalent, the bonding is weak intermolecular forces between the molecules. For giant covalent is strong covalent bonds between the atoms. Okay, then for structure, there are many ways you can describe structure. So first you have the main 4, which is your giant ionic lattice structure. That is for ionic compounds. Then you have your simple covalent structure or simple molecular structure. Then you have giant covalent structure. Then you have giant. Okay, I'll go through the metal one later. Okay, so these are the 4 main structures that you can mention. But under giant covalent, you have diamond, right? Diamond can be tetrahedral structure also. And then you have graphite. Graphite can be hexagonal. Okay, so these are the main ways you can use to describe structure. It is just to help you out for your questions. Okay, so let's move on to metallic bonding. Okay, will any of the questions ask us about similarities between graphite and diamond? Okay, so your question is almost the same as, are there any similarities between giant covalent compounds? So of course there are, right? So if we look at the notes, right, graphite and diamond are both giant covalent substances. So you just need to state what all giant covalent substances have in common. So first thing is the strong covalent bonds between atoms. Okay. Then the second thing is high melting point. Okay. And yeah, that's about it. Because the others are all different. Okay. So talk about the bonding. The bonding is always the same. Okay. Now we move on to metallic. So metals, right, they have the tendency to lose electrons. Okay. So when they lose electrons, they become positive ions. So in metals, the lattice, right, it consists of positive ions surrounded by sea of delocalized electrons. So how do I picture this? Think of it like a honeycomb. Okay, my drawing is not very good, but something like this. Okay, let's say this is a honeycomb. And then what surrounds the honeycomb? A lot of bees, right? So you have all these bees surrounding the honeycomb. So I draw bees as this line over here. So the honeycomb is basically your positive ions. It's stuck there. Okay. And then the bees surrounding the honeycomb is the sea of delocalized electrons. Okay, so the bees over here are your electrons, and the middle here is your positive ions. Okay, so that is basically the structure of, the bonding of metals. Okay, so metallic bonding is strong electrostatic force. Strong electrostatic force between the sea of delocalized electrons and positive ions. So you realize we use electrostatic again. For ionic compounds, we also use electrostatic. So what's the commonality here? It's the charges. Whenever we talk about charges, we talk about electrostatic. Okay, so what are the charges here? You have positive, you have neutral, you have negative. So positive and negative, like I mentioned earlier, they will have very strong forces together. Okay, so we have positive ions here. And electrons, right? What are the charges of electrons? It's -1, correct? So that is a negative charge. So again, you have positive charge, you have negative charge, then you have strong electrostatic force. Okay, so that is metallic bonding. That is also why the bees over here, right? They always swarm around they always crowd around the honeycomb. Okay, so it's like very strong attraction, very strong electrostatic force. Okay, so the free electrons or delocalized electrons are able to move about freely. Okay, which means that it can conduct electricity. Okay, but the positive ions, right? They are just stuck there. They cannot move. Okay, so only the electrons are free to move. The positive ions are not. Okay. So the strong electrostatic force between the positive ions and the sea of delocalized electrons give rise to a giant metallic lattice structure. So it just tells you this is the structure of metals. Okay, so you're gonna write this if the question asks you to explain in terms of structure, okay, or describe the structure. So metals have these properties: high melting and boiling point, because it has strong metallic bonds, right? Because the electrostatic force between the positive ions and delocalized electrons. So it has strong metallic bonds, a lot of energy is needed to overcome. Okay, so it's high melting and boiling point. Good conductor of electricity and heat. Okay, again, two things, ions and electrons. Which one does it have? It has electrons that are free to move. Okay, it also has ions, but the ions are not free to move. Okay, so only the delocalized electrons can move about to conduct electricity or transfer heat. Okay, lastly, they are malleable and ductile. So malleable means that can be bent without breaking easily. Okay, then ductile means that put into a thin wire without breaking. Okay, that means I can literally pull a metal. If I have enough force, I can pull a metal into a thin wire without it actually breaking. Okay, so it'll still be intact. So what's the reasoning behind this? Is the layer of atoms, right? They are in a very orderly arrangement, okay, for metals. So for orderly arrangement, they can slide over one another easily without disrupting the metallic bonds. Okay, why does the metallic bonds not get disrupted? Because the metallic bonds is between the positive ions and the free electrons. It's not between the atoms. Okay, so I hope this is clear. The metallic bonds between positive ions and free electrons. So no matter how much the atoms slide past each other, the metallic bonds will not be disrupted. Those free electrons are always there. Okay. So can you guys try questions 7 and 8? So for this one, I'll give you 4 minutes. So I'll be back at 9:20. So we know that the structure is a positive ions surrounded by C of D localized electrons. So you can draw like 6 positive ions and like 10 10 electrons can already. You don't have to draw so much. Okay, so you can draw like this part. Draw like that can already. If the question asks you, you don't have to draw so big. Yeah, no problem. Okay, now it's 9:20. Let me go through the questions. Can metals conduct electricity? Why or why not? Okay, so conducting electricity, conducting electricity, it either has to have free ions or free electrons. So metals, they have, what's the structure? Positive ions surrounded by free of D localized a sea of D localized electrons. So the electrons are free to move, but the ions are not. Okay, just like the honeycomb. The honeycomb cannot move, but the bees surround the honeycomb can move. So yes, because they are free moving electrons. C is your answer. Okay, not because they are both. A is wrong because it says yes because they are free moving electrons and ions. Okay, but no, there's only free moving electrons. And then B is wrong because it says free moving ions, but no, the ions are not free to move. Okay, C is the only correct answer. And D says no, so D is wrong also. Okay. Question 8. The diagram below shows a giant metallic lattice. Describe this type of bonding in metals. Okay, so when they ask to describe, it's very simple. Just have to say this bonding consists of positive ions. Okay, so your gray circle here, positive ions, surrounded by C, a sea of delocalized electrons. Okay, that's it. Okay, are there any questions so far? Okay, then we are actually done going through everything for today. So let me just do a little plug here. So our class, right? We're actually giving 20% off your first month to the first 5 students who enroll after this crash course. Okay, or this month. So normally we charge $80 for 2 hours of lesson. Okay, which is what I'm giving you today for free. Okay, but there's a 20% off your first month. So 1 month there's usually 4 lessons. So it equals to 320. Okay, so 20% off, it will become 256. Okay, for 4 lessons. Or if you just want to have a trial lesson to test out another lesson, is 64. Okay, so it's a 20% off discount for the first 5 students. So if you found this useful and you want to continue lessons, you can just sign up the link here. After this is over, you can sign up. So it's tinyurl.com/sign-up-chemistry-LCH. Okay. And we open a new available class for Sec 3s. Okay, because all our Sec 4 slots are full already. So only for Sec 3s, we have a new available class on Sundays, 3 to 5 p.m. Okay, and what you can expect is that all lessons will be recorded. So like this crash course today also is recorded. Okay, so all of lessons are recorded. So if you CMI for anyone, if you cannot make it, then you can rewatch the lessons. But of course, I recommend everybody make to the lessons because it will be quite interactive. Okay, and then we also provide WhatsApp support. So it's like customer service. You have any questions, you just ask me on WhatsApp, then I'll reply as soon as possible. Lor. Okay, and the reply won't be like very short. I will try to be as specific as possible. Yeah, and explain the answer. Okay, so this, if you're interested, you sign up via tinyurl.com/signup-chemistry-LCH. Okay,